Hey everyone, this is Ayush, and in this video we will learn about sparse table. Well, sparse table is a range query data structure which is used for performing range queries efficiently with an time complexity of log n and big of 1 depending upon the type of function. So let's start this video first by understanding that what is the need of an sparse table. Okay, let's say we have this array, and on this array I ask you to answer the range minimum queries. Let's say I want the range minimum from index 1 to index 4. In this case, what you need to do, you need to simply iterate from index 1 to index 4 to find the minimum. So for this query, your answer will be 3. Similarly, for 2 to 5, you need to iterate from index 2 to index 5 and your range minimum will be again 3. Well, if we talk about time complexity, then in worst case, you need to iterate from the first index to last index. So for answering each query, your time complexity is big of n. And let's say I give you q queries, then in that case, the overall time complexity will become q times n. Now, if you want to optimize this time complexity, and if we carefully observe, we cannot optimize this factor because there's a number of queries which will be constant. All we have to optimize is this n, that we need to find a way somehow to answer queries in less than n time. Okay. Now, some of you may think that can we build a prefix minimum array? The answer is no. You cannot build a prefix minimum array to answer queries in big of 1 because the behavior of minimum function is completely different as compared to addition or XOR. Because in case of an addition and XOR, we usually build prefix arrays, and to remove the contribution of L minus 1 part, we simply subtract or take a XOR. But in case of minimum, you cannot do anything. There is no way to remove the contribution of minimum of elements from index 0 to index L minus 1 if you build an prefix minimum array. So what we can do, we have a solution sparse table which will answer our queries in big of 1 and log n. So let's see how a sparse table is built and how it processes the queries. Let me erase this. Okay. So this is how a sparse table looks. You can see it's a 2D matrix of integers. Let me first explain you how we denote a sparse table. A sparse table is denoted by a 2D matrix of integers. Let's say the name of our matrix is SP. Then we denote it like this, SP of I, comma j. Now this is one element from the sparse table, but what this element denotes? This element simply denotes that from ith index, we consider a segment of length 2 to the power j. That's it. This element simply denotes this, that from ith index, we consider a segment of length 2 to the power j. And in this element, we store the answer of that segment. For example, if my I is 3 and let's say my j is also 3, then this term will simply denote a range starting from ith index, that is 3, till 3 plus 2 to the power j, that is 2 to the power 3. Okay, so it will be simply 3 comma, this is 8, 9, 10, 11, but we need to write 10. Okay, add a minus 1 out here. So this is what a term from a sparse table denotes, that a range starting from ith index of length 2 to the power j. Okay, and for this range, we'll simply store the answer in this cell. Now, let's say we have built a sparse table for answering range minimum queries or range minimum queries. Then this cell will store the minimum of range from index 3 till index 10. Or if we have built a sparse table for answering range maximum queries, then this range will store simply the maximum over a range from index 3 to index 10. Okay, let's see now how a sparse table is built. Even you will get the answer that why we have considered powers of 2 while making n segment. There's a reason behind that we have considered powers of 2. But first, let's understand how a sparse table is built. Then we will see how queries are processed. Then you will come to know that why sparse table is built in this way, like by considering the powers of 2. Okay, so let's say we have this array, and on this array we need to build a sparse table. On the left side we have indices from 0 to 9, and on the right side at top we have the powers of 2, that is j. We only need a third power of 2 because third power of 2 is 8 and fourth power of 2 is 16, but the length of our array is not that large. So that's why we have only considered till j equals to 3. Now, a sparse table is always built from smaller powers to larger powers. Like first we will build sp of I comma 0. 0 means 2 to the power 0. We will first calculate for each index the answer within a segment of length 2 to the power 0, that is 1. Then we will construct the answer for j equals to 1, that is a segment of length 2. Then for j equals to 2 for a segment of length 4, and so on. The reason is also simple. The way we calculate the answer, we need smaller powers of 2 to be computed first so that we can compute the larger powers. I will tell further in video the why we compute smaller powers. Now observe here, for I equals to 0, we need to consider a segment of length 2 to the power 0, that is 1. So from 0th index, a segment of length 1 is the element itself. So for the element itself, the minimum is the element itself, that is 3. Similarly, for first index, it will be 7. For second index, 2. Third index, 8, and so on. So in the first row, we usually put the elements directly because the length 1 segment is the element itself. The actual calculation starts from the j equals to 1, because from j equals to 1, we need to consider segments of length 2. Now, you can see here, from I equals to 0, a length 2 segment is 0 to till 1. So for this segment, the range minimum is 3. From I equals to 1, that is from 7, a length 2 segment is 1, comma 2. And for this segment, your minimum is 2. Similarly, from second index, the length 2 segment is 2, comma 3, and its minimum is again 2. And so on for rest of the elements. Now again, if we consider j equals to 2, that is, we need to consider segments of length 4 from ith index. From I equals to 0, a length for a segment is 0, 1, 2, 3, that is 0 to 3. And for this segment, its minimum is 2. Yeah, here. From I equals to 1, a length for segment is 1, 2, 3, 4, and its minimum is 1. From I equals to 2, a length for segment is 2 to 5. And for this segment, the minimum is again 1. Okay. So in this way, usually a sparse table is built. Now, let me show you the formula which we use while coding to calculate these terms, because now someone will ask that, okay, let's say we are considering j equals to 3, that is a segment of length 8, that is from 0 till 7. Here, I orally tell you the answer that minimum is 1, but while coding, how we usually calculate this answer? Because if we need to iterate over the segment, then there's no use of taking sparse table in consideration because we need to optimize that n factor. And if we are still iterating over the elements, then we don't optimize our n factor from the time complexity. So here you will get the answer of your question. So why we compute smaller powers first and how current answer is calculated. Let's consider SP of, I'm writing a generalized term I comma j. Now we need to calculate the answer from ith index for a segment of length 2 to the power j. Um, Let me consider a segment. Let's say I is 1 and j is 3. Okay. Now for this segment, we need to calculate the answer. Now tell me one thing. If we are calculating answer for j equals to 3, we have already calculated answer for j equals to 0, 1 and 2. Okay. Since we have already calculated answer for smaller segments, we will take help from to calculate our current answer. How? Now we all know that 2 to the power 3, 8 can be constructed using 2 powers of 2 to the power 2. Because once you multiply 2 to 2 to the power 2, you get 2 to the power 3, that is 8. So your current power of 2, that is 2 to the power j, can be constructed using 2 powers of 2 to the power minus 1. Okay, like 4 plus 4 equals to 8. And we all know this. So let's use this fact for calculating the answer. How? For this length 8 segment, what I am saying, let's use two segments of length 4. Let's use these two segments 1, 2, 3, 4, 5, 6, 7, 8. Because we need minimum from index 1 to index 8. And we have already calculated the answer for the segments of length 4. That is this segment and this segment. And we can simply combine their answer in big of 1. And for our current cell, we will simply calculate our answer in big of 1. So instead of iterating over the elements, in big of 1, we will get our answer. But how we will combine the answer? We need very simple and small maths for this. Now, you need answer. We are calculating the answer for I equals to 1 and for j equals to 3. Okay. And to compute this answer, we will be using segments of length j minus 1. Sorry. See here, what we can simply do, we need to consider SP of I j minus 1 first. What this term denotes? This term denotes a segment starting from index I having a length of 2 to the power j minus 1. That is, in this case, it will be 2 to the power 3 minus 1, 2 to the power 3 minus 1, that is 2 to the power 2, which is 4. Okay. So we will consider a segment of length 4 starting from index 1. That is 1, 2, 3, 4. But we need one more segment of length 4. And tell me one thing, from where this segment will start. If I'm on ith index, I consider the first 4 elements. The next 4 elements, of course, starts from the index I plus 4. That is, in this case, I is 1 plus equals to 5. It will start from 5th index. And from 5th index, you have to again consider a segment of length 4. So for that, mathematically, we will write like this. SP of, from current index, you need to move 4 elements ahead. And 4 is nothing but your 2 to the power j minus 1. And here, We need to consider a segment of length 4, that is again j minus 1, and we will simply take the minimum. Remove this addition sign. We will simply take the minimum of this 2, and we will get our answer. That simple it is. In this way, we can get our answer in big of 1. Let's understand this again by taking one more query. Say we need to compute the answer from third index and for j equals to 2, that is for a segment of length 4. For this segment, we need to compute the answer. Now, what I said, for computing an answer for 2 to the power j, we should consider two segments of length 2 to the power j minus 1. That is for 2 to the power 2, 4, we should consider segments of length 2 to the power 1. That is 2 length. So we need these two segments to compute our answer. 3 to 4 and 5 to 6. Let me shift this below. Okay. Now how will you calculate? You will write simply SP of from third index for j equals to 2. That is a length 4 segment. We need to consider two segments of length 2. Okay. Of course, we are standing on index 3. We need to calculate a answer for a segment of length 4. For calculating that, we are considering two segments of length 2. From third index, we will consider first segment of length 2, which will be SP of third index. We need to write 1 here because 2 to the power 1 is 2 to the power 1 is simply 2. Okay. This will consider this segment. And for considering this segment, tell me one thing. We have considered first two elements. We need two more elements. Okay. So if I'm standing on index 3 and I have considered first two elements, I need to move two elements ahead. So we need to simply write comma SP of 3 plus to move two elements ahead. In terms of j, we will simply write it 2 to the power j minus 1. Okay, because j's are 2, 2 minus 1, 1, 2, 3 plus 2, 5. We will start from fifth index and we need to consider a segment of length 2. That is again 2 to the power j minus 1, but we will simply write j minus 1. That is j is 2. Here we will write 1. Even you can write it simply 2. Okay. So in this way, in big of 1, we calculate the answer for each cell in a sparse table. And that simple it is. So this is a way by which we build a sparse table. At first it looks a bit confusing that I'm considering a parse of 2 just by writing 1, 2, 3. If you are still confused, I recommend you to rewatch this part. If you watch 2 or 3 times, you will definitely not having any doubt on this part. Now let's see how queries are processed in a sparse table. Once we build this structure, now we need to answer the queries. The most important reason that we build a sparse table is to answer our queries. Now, how a sparse table will answer our queries? Let's consider for this array, I gave you a query from index 1 till index, let's say 7. Okay, I need answer for this segment. We need to calculate the answer for 1 comma 7. Now, earlier what we were doing, we were simply iterating. Let me see whether the video is recording or not. Yes, it is recording. Now earlier what we were doing simply, we were iterating from index 1 to index 7. But now we have the structure. Let's see how this structure will help us instead of iterating, how we can find answer quickly. What is the length of this segment? 1 to 7, we have total 7 elements, that is r minus l plus 1, that is 7 minus 1 plus 1 equals to 7. This is the length of my segment. Okay, this is the length of my segment. Now let's write this segment in binary format. The binary representation of 7 is something this: 1 1 1. We have zeros ahead. This is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, and this is 2 to the power 3. I'm not writing all the bits till 31. Okay. Now you will also know why we have built a sparse table in powers of 2. Now let me draw a number line also for a better understanding. Here we have 0, 1, 2, 3, 4, 5, 6, 7, 8. And we need to compute the answer for this range. Starting from 1, ending till 7. Okay, fine. Now tell me this length, this segment 1 to 7 has length 7. Okay. Now this 7 is constructed using this parse of 2. Any number we have is always constructed using a parse of 2. If you write binary representation of any number, let's ignore 7 for a while and let's write this 110. Now this is a binary representation of 2 to the power 1, 2 to the power 2, 2 to the power 4, that is 21. This is the binary representation of 21. And here we can simply see that 21 is constructed using the 3 powers of 2, that is 2 to the power 4, 2 to the power 2, and 2 to the power 1, that is 16 plus 4 plus 2 equals to 21. Every number in maths, not number, I will say an integer, is constructed using this powers of 2. Okay. Now what if I say using this powers of 2, we will simply calculate our answer. Let's see how. Similarly, 7 is built using 3 powers of 2, that is 4 plus 2 plus 1. 7 is constructed using this powers. Now, using this power, we will calculate our answer. How? Tell me one thing, in sparse table, we have calculated the answers for variable length, but all those lengths are also the power of 2. All those lengths are power of 2. Now let's see how those powers of 2 will help us. I'm standing on index 1. For index 1, I have calculated 2 to the power 0, that is answer for this segment, 2 to the power 1, that is for a length 2 segment, 2 to the power 2, that is the answer for a length 4 segment, 2 to the power 3, that is the answer for our length 8 segment. Well, now tell me one thing, naturally, we need to go till this. So considering the segment of length 8, that is for j equals to 3, is not worth it because we need answer till 7th index, but it has calculated the answer till 8th index. Okay, so we will not consider that segment. Even considering a length 1 segment and length 2 segments, we can consider them, but we need to calculate the answer as early as possible. So considering the longest segment will help us. Okay, considering the longest segment will help us, because if you consider this segment, you need to calculate the answer from 3 to 7. If you consider this segment, you need to calculate the answer from 2 to 7. But if you consider this segment, we need to calculate the answer for only 3 elements, that is from 5 to 7. So we will consider the longest segment. That is 1 to 4. And we have its answer stored in SP of 1, and this is a segment of length 4, that is 2 to the power 2, so our j is 2. Okay, so it is stored in SP of 1 comma 2. We will consider this part. Now since we have calculated answer till 4, we will move our pointer or our current I from I equals to 1 to I equals to 5. And as you can see, we can relate this with here, that we have simply calculated the answer for segment of length 4. Now we are left with only two segments, a segment of length 2 and segment of length 1, that is 2 to the power 1 and 2 to the power 0. Similarly, we will do here for I equals to 5. Of course, we have calculated different segments of length 2 to the power j, that is length 1, length 2, length 4. But here in this case, considering a length 4 segment will not help us because it is going from 5 to 8, but our query is ending on 6. So the longest segment which will help us is a segment of length 2, that is 5 to 6. Okay, and this segment, let me write here. We have considered a segment already of length 1 and 2. Now we have to consider one more segment of length SP of 5 comma 1. Why 1? Because we are considering a segment of length 2, that is 2 to the power 1. Now move your pointer from index 5 to index 7, and we have considered a segment of length 2 also. Now again for index 7, we have segments of length 1, 2, 4, 8, but we will only consider the segment of length 1 because the length 2 segments goes out of our range, but the length 1 segments fits in our range, and it is the last segment which we need to consider because we have already calculated the answer for elements 1 to 6. Now we are only left with 7. So we will simply write SP of 7 comma 0. Why 0? Because 2 to the power 0 is 1 and we are considering a segment of length 1. And we need to take the minimum of these three elements now only. That's it. Earlier we were iterating over all the elements, but now we will get the answer using only these three elements because these three elements constitutes the answer for complete range from 1 to 7. Let's take one more query. I know still it will be not clear for a lot of folks. And as you can see, if we move using sparse table also, for 1 to 7, the minimum is 1. And since we have considered this four segments, SP of 1 comma 2, that is 1 comma 2, we have to take minimum of this. Then SP of 5 comma 1, that is this one, and SP of 7 comma 0, that is this. And minimum of these three elements is also 1. So we have verified our answer using our sparse table also. Well, let's say now if I ask you to answer the query within a range from um, let's take let's take a big length. I think it will be more clear in that case then. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and let's say 14. For better understanding, I'm considering a bigger number line, and let's take a range of length from 3 till 14. Let me draw here. I need the answer in the range 3 to 14. Okay. Now again, the brute force way is to iterate from index 3 to index 14, but we don't want to iterate over all elements. What we can do simply, what is the length of our segment? 14 minus 3 plus 1. That is 14 minus 3, 11, 12. No, I don't want a segment of length 12. Wait. Let's consider till 13 only. Let's consider till 13 only. So length of my segment will be 11 now. That is r minus l plus 1. My length will be 11. What is the binary representation of 11? The binary representation of 11 is 1, 0, 1, 1. That is 2 to the power 3 plus 2 to the power 1, 8 plus 2, 10 plus 2 to the power 0, that is 1. Now tell me one thing, in sparse table, we have already calculated the answers for this length segments. So we have to only find the answer for these three segments. Instead of iterating over all the 11 elements, I will only consider these three segments. And you can simply see 2 to the power 3 is 8. Since we are starting from third index, we need to consider a segment of length 8 from here. It will be till, it's 8 now. 1, 2, 3, 4, 5, 6, 7, 8. It will be till 10. We will consider a segment of length 8. But if you subtract 8 from 11, we are still left with 3. So 3 is made using the power, 3 is made using the powers of 2 to the power 1 and 2 to the power 0. So we need to consider a segment of 2 to the power 1 again, that is from 10 till 11. And but still 3 minus 2 is 1. We have already find the answer from index 3 till index 11, but our range is still 12. And as you can see, we are left with only segment of length 1. So we need to consider this segment also. Okay. I think there's something wrong from my side. It will be from 11 to 12 and there will be a length 1 segment. Okay. So what I said, we need to answer the query in the range 3 to 13. The length of that segment is 11. Binary representation of 11 is this. And we saw that 11 is made using the powers of 2, that is 8, 8, 4 and 1. Sorry, 8, 4, 1, not 8, 2 and 1. So what I said, if we have already calculated the answer for this segments, we will only consider them. Instead of iterating over the 11 elements, we will consider only these 3 elements, because if we consider only these 3 elements, they will give us the answer for complete range. As you can see, 8 is from 3 to 10. Your length 2 segment is from then 11 to 12 and length 1 segment is for 13. So if we consider these 3 elements, because this range has answer for 3 to 9, this has for 11 to 12 and this has for 13, we will get the answer for 3 to 13. Now how to write this mathematically? We have to consider a lengthed segment from index 3. You will write simply SP of 3. A lengthed segment is simply length 8 segment, that is 8 here. We won't write 8 here, we will write 3 because 2 to the power 3 is 8. We need this term, comma. Now tell me one thing, we have considered 8 elements starting from index 3. Now we need to consider the rest of the elements from 11 to 12, 13. So we will move 8 elements ahead. So move your I from 3 to 11. So it will be now 11. We need 2 to the power 1, that is 1. Now this will give us answer for 11, 12. But we need one more segment of length 1, that is 2 to the power 0. So SP of, and it is starting from 13. So by considering only these three elements, we will simply get our answer. So this is how queries are processed within a sparse table. Now you will say that Ayush, we are still iterating over the elements. Although we are iterating over less elements, but we are still iterating over the elements. Yeah, I agree that we are still iterating over the elements, but observe on how many elements we are iterating. Okay, let's discuss the time complexity and space complexity also. I hope now you guys get why we have built a sparse table in a powers of 2. The reason is simple. Whatever query you will have, its length will be integer, and an integer can be always represented with the help of powers of 2. Okay, if an integer can be always represented using the powers of 2, then it's better that if we compute the answer of compute the answers for all the segments of powers of 2, we have to just consider some segments from that, or some segments of powers of 2 which are contributing to make that particular integer. Now let's discuss its time complexity. What we are doing for each index, we are calculating answer in big of 1. As I showed you earlier, using this formula. See, this is the formula. They have in this image, they have denoted this sparse table with ST. So ST of I comma j is minimum of ST of I j minus 1 and I plus 2 to the power j minus 1 j minus 1. Okay, we have already seen about this formula. So using this formula, we calculate our answer in big of 1. There are n elements. For each element, we are considering the segments of power 2. Let's consider this I equals to 0. We have considered a segment of 2 to the power 0. We have considered a segment of length 2 to the power 1, then 2 to the power 2, then 2 to the power 3, and that's it. We won't consider 2 to the power 4 because it is 16, but our array is not that large enough. Well, in worst case, tell me one thing. Our integer is made up of 31 bits. The 32 bit is sign bit, so it is made of 31 bits. If you also ignore that bit, still we have 32 bits. Okay, we have total 32 bits. And in worst case, imagine we got a segment whose length is made by using all the powers of 32. Like its binary representation is like this. There are all ones in its binary representation. Let's say this is 0th bit and this is the last 31st bit, that is 32 bit if we do one base indexing. It has all ones in its binary representation. Then see carefully, in worst case also, we will be iterating over only on 32 elements. We were we will iterate on 32 elements. Usually we don't get that large arrays in input because this will be something I think greater than 10 to the power 9. Okay, and you see, just observe that for this huge array, the largest query which we can get, not exactly of this size, it is of course greater than this, but for this huge array, even if you get the longest query, you will be just iterating over 32 elements, not all the 10 to the power 9 elements. And that is how efficient our sparse table is, because all the number is made using powers of 2. and we have already calculated for powers of 2 the answer. So you have to just add them. We have to just consider them in our particular function, minimum, maximum, GCD, whatever it may be. So this is the power of a sparse table, that for this huge array also you will be iterating over only on 32 elements. So what will be the time complexity of answering each query? Let's first see what will be the time complexity of building a sparse table. Now tell me one thing. From each index, you are left with a segment. From index 3, you are left with a segment of length n minus I. N minus I, that is n is 9, and 9 minus 3 is 7. 1, 2, 3, 4, 5, 6, 7. Yeah. You are left with a segment of length n minus I. From each index, you have a segment of length n minus I. Now, for a segment for length n minus I, let's say I call it capital L, you will be finding answers for segments of length 2. Okay. Now, how many times you need to calculate the answer for a particular I for different parts? Of course, this L is made using some powers of 2. So, okay, some powers of 2 are used to construct this particular length or this particular length segment. In school, we have learned a simple formula that for any number, we have log. What log tells us that how many powers of B are required to reach A. What this simply means that we need K powers of B to reach A. Correct? Now, as we know, every number is constructed using powers of 2. Every number is constructed using powers of 2. So we will be needing some K numbers of 2 to reach that particular number N. Correct? So if I write like this, 2 and this L, it simply says that we need K powers of 2 to reach L. We need K powers of 2 to reach L. Even we can say from this that if you will divide L K times, you will get 1, because your L is made using K powers of 2. So if you divide your L K times by 2, you will simply get 1. Correct? Then from this, we can simply infer that for any segment of length L, at max, you will calculate the answer, or you will calculate the segments that will be always log L to the base 2. Log L to the base 2. I know it's confusing. Let me repeat it again. Let me repeat it again. There are total n elements. There are total n elements. For each element, we are considering some segments of 2. Now tell me one thing. Your time. What will be your time complexity? Since there are n elements, and for each element, let's say in worst case, we consider k segments of length 2. Your time complexity will be n times k, because for each segment you are calculating answer in big of 1, and for each element you are calculating answer for k segments. Then for n elements, you will be calculating answer for n times k segments. Correct? Now we just wanted to know what is this k. What is this k? So what I said that for any index I, we are left with a segment of length n minus I. We are left with a segment of length n minus I. Let's say this n minus I is equals to L. Okay. Now for these long segments, we need to consider different segments of powers of 2. Okay. Just give me a minute. Just give me a minute. Let me think. to tell this you in an easier way. Um, okay, fine. So for any index I, you are left with a segment of length L, and for this L, we will consider different powers of 2. Now, even this L is constructed using powers of 2. Okay, some powers of 2 are required to construct L. Listen carefully from here that some powers of 2 are used to construct L. Now, we have this logarithmic formula which simply tells us how many powers of 2 are required to reach L. Correct? How many powers of 2 are required to reach L? For example, log 16 to the base 2 is 4. You need 4 powers of 2 to reach 16. Log something 25 2 is also 4 point something. That you need 4 powers of 2, and then you need some extra elements to reach 25, or you can we simply write it approximately 5. Correct? If you consider 5 powers of 2, that is 2 to the power 5, of course it is 32 greater than 25. But if we consider this many powers, we will definitely cross the length 25. That is what this log term tells us. So if I need this many powers to construct L, so of course we will be having this many segments also within that particular L. Let me draw this so you guys will get a good understanding. We already have here a number line. What I'm saying, any number is constructed using powers of 2, and the number of powers of 2 required is this many. And what I'm saying, we will be always iterating this many over this many segments for each I. So our overall time complexity is n times log inverse case length will be n. This will be our time complexity for building a sparse table. Now let me show this with the help of a diagram. Let's say our um, let's say in worst case our length is 14 or 15. Okay, this is a 15 length array. Our n is 15. Now, if you start from zero, of course, from zero we will get most number of segments. If we start from 1, 2, 3, 4, with respect to them, starting from zero will give us the more number of segments. If we start from zero, see here, this is the power of 2 we can consider. That is 2 to the power 3. We cannot consider a power more than that because it will go out of our range. Then from 9, we will go till somewhat 12. That is 2 to the power 2. Because if you consider 2 to the power 3, again we will go out of range. Then again you will consider a segment of length 2 to the power 1. Actually, I have drawn wrong. This will go till 7 only. Then this will go from 8 to 11, that is 2 to the power 2. This will go from 12 to 13, that is 2 to the power 1. And this will be for 14, that is 2 to the power 0. Now see here, our number is constructed using power of 2. And that is what I am saying, that we need this many powers to construct our number. Equivalently, we have this many segments to calculate for that particular I. And you can see we have only this many segments, that is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. We cannot consider 2 to the power 4 because it is 16. But we have a segment of length 15 only. I hope now you get this part. It is a bit confusing, but rewatch this part again. You will definitely get how the time complexity of building a sparse table is this. Okay, so this is the time complexity of building a sparse table. Okay, I haven't read it here. We will see what is this log array when I will show you the implementation of sparse table. Now let's discuss the time complexity of queries. That what is the time complexity of processing the queries? Tell me one thing. For any query, we are considering its length, and it's how many elements we are considering, on how many elements we are iterating. The number of elements are equal to the number of parts of 2 required to construct that number. Okay, let's say we have binary representation this, we will be iterating over 1, 2, 3, 4 elements. So we are iterating over the number of elements or the number of powers which are required to construct that element. And we have already seen that for constructing any element, we need this many pass. So of course, the time complexity of answering our query becomes this, where n is your length. Okay, n is your length of query. Because it's simple. See, you are considering number of elements for iterating, which is equal to the number of parts of 2 required to construct that number. And for any number to construct it using parts of any particular number, let's say we have number n, we have to construct it using parts of c, we need total log n to the base c parts to construct it. Similarly, if we are considering parts of 2, we need total log n to the base 2 parts to construct that number. Okay, so that's why our time complexity is log n to the base 2. Now, there's a catch. If you remember what I said at the start, that sparse table we can answer queries in big of 1 also. We can answer our query big of 1 also. But here we have discussed that we are answering queries in log n. But how we can answer queries in big of 1? Let's see that part. There's a concept of idempotent and non-idempotent functions, but before explaining the concept, I would like to simply show you from diagram. For calculating the number, we are iterating on some parts of 2, correct? We are iterating on some part of 2. But now what I am saying, we don't need to iterate on parts of 2. We just need to consider 2 elements for constructing our answer. Let's see how. Say we need to construct our answer, or we need to find our answer for a segment starting from index 1 till a segment to index 13. Now the length of this segment is 14. The binary representation of 14 is about 1110. You need to iterate on 3 elements. Okay, but what I'm saying, you don't need to iterate on all these elements. What you can simply do from this one, I'll ask you a question. What is the length of longest segment you can consider, which is power of 2, given that which is a power of 2. So from 1, you can consider a segment of length 8, which will go till 9. You cannot consider a segment of length 16 because it will go out of our range. Now again I'm asking, now tell me one, if you consider, for this, what do we need to write? We need to write sp of 1 comma, and this is somewhat 3. Now we need only one more term to calculate our answer. We need answer for this many elements. Okay. Array is ending on 13. So let's go to 13 directly, and I'm asking a simple question. Now, we will not get into a maths that okay, we have considered elements. Now we need to consider only three or four elements. Not like that. I'm asking a very simple question. What is the longest segment in powers of 2 which we can consider in backward direction from 13? And that is of length 8, which will go till 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, which will go till 6. Okay, so it will be SP of 6 comma 3, or you can simply add 6 as 13 minus 8. Now, tell me one thing. Instead of iterating on k elements, if we consider these two segments, we will get our answer, because this segment is giving answer for the range or giving minimum for the 1 to 9, and this segment is giving us the minimum in the range 6 to 13. So if we combine their answer, we will be having a minimum in the range 1 to 13. Isn't that simple? Instead of iterating over all the elements, we need to just consider two elements, and in big of one, by combining them, we will get our answer. That simple it is. So in this way, we can answer queries in big of one using a sparse table. But there's a catch also. It is not applicable for the functions. We will see that ahead. But I wanted to show you this, that how we calculate the answer in a big of one for any range. Now it doesn't matter what range you have. It doesn't matter what range you have. Let's say it is starting on 0. It is 0 and is 10 to the power 5. Okay. Here you have 1, 2, 3, and here are some elements. Here you have 10 to the power 5 minus 2. Here you have 10 to the power 5 minus 1 and 10 to the power 5. Even if I ask you to answer the query 0 till 10 to the power 5, okay, of course you will be taking out 10 to the power 5 base 2 elements, which is something this 5 will go ahead. Property of log 5 times log 10 to the base 2, and this comes out to be, I think this is somewhat 3 point something, so 5 into 3 point something. Approximately you can consider you are iterating over 16 elements. As a segment of 10 to the power 5, you need to iterate over only on 16 elements, and that will be some powers of 2, which comes in the binary representation of 10 to the power 5. But instead of iterating over 16 elements, we will just consider two elements. And what are those two elements? Consider the longest power of 2 starts from our starting index L, and which fits in our range L to R, and it is a power of 2. It will be something like this. Again, consider a segment. This is not a power of 2. I don't know 10 to the 5 minus 2 is a power of 2 also. Just for explaining, I am telling. Now consider from our R the longest segment, which is a power of 2 and which is in our range. It will be something like, so we have answer from 0 till something k index, and we have answer from this R till some R in some. Just combine these answers. You will get the minimum for complete range, and that simple it is. Now you are just calculating answer in big of one. Okay, so in this way, guys can simply calculate answer in big of one. Now we need to discuss only some one or two things, then we will move to the implementation part directly. The first constraint is that you cannot use a sparse table for answering dynamic lists. It simply means that if your array is changing, you have updates also, you cannot use a sparse table. Now just ask yourself why. Just ask yourself. We see how we are constructing sparse table. If tell me a single element also changes, we need to construct the complete structure again, because the single element is giving distribution in lots of segments. zero lot segments are starting, from what sub segments are starting. We need to construct the complete structure again. And constructing a sparse table again is n times log n work. Okay. And if for each query you are doing this much work, then it's worse than earlier, because brute force we were just iterating on n elements. Because but construct your sparse table again and you will query it, then there is no meaning of using a sparse table. So right, you cannot use a sparse table for answering dynamic queries. Your data structure must remain constant from the start of your query till end of your queries. Okay, that is the constraint which you have to keep in your mind while using a sparse table in any question, that queries must be static queries. Elements should not change on the data structure which you are considering these queries. Now the second constraint, you will ask you will ask Ayush, you will ask me that for which functions we can do use that big of one formula which I told, that consider the longest power of 2 from L, consider the longest power of 2 from R, and just combine them their answers. Tell me one thing, can we use that for addition? No, you cannot use that for addition, because see now, there is a big overlap in those two segments. If we do it for addition, we will get wrong answer, because we will get addition of these elements, we will get addition of these elements, but we will get twice the addition of these elements. So for addition, you cannot do that. Even for XOR, you cannot do that, because for XOR also, we'll get the XOR of this elements, we will get the XOR of this elements, but we will get twice the XOR of this elements, and it will cancel out the XOR. As we know the property of XOR, with same element XOR is 0. So we are only left with the XOR of this part and this part. So we cannot use this formula for addition and XOR. Can we generalize this? Yeah, we can generalize this. In maths, there are two famous terms, idempotent functions and non-idempotent functions. What are idempotent functions? Idempotent functions are those functions, let me write here, idempotent functions. I hope this is correct spelling, idempotent. Oh, I think, yeah, idempotent functions. What the definition of idempotent function says, your output won't change if you keep adding same input. Output won't change if you keep adding same input. What comes in the idempotent functions? Minimum, maximum, GCD. Now for this, let's say I have my five, like I have 5. Now keep adding same 5. Keep adding means keep giving 5, same 5 as input, same data as input. Your output won't change. Your minimum will be always 5. Your maximum will be always 5. Again, for let's say we have 5. If you keep giving 6 again and again and again, your minimum, maximum, GCD will never change. Your minimum will be always 5. Your maximum will be always 6. Your GCD will be always 1. Nothing will change if you keep giving same input. Such type of functions comes under idempotent function, but that is not the case for addition. If I add 6, you will get 11. Okay, let's add a 6 again. Will it be 11? No, it will become 17. Add in 6 again, it will become 23. In case of XOR also, let's say I have a 5, XOR it with 6. I think it is somewhat 101110. This will get cancelled. We get 3. Now again XOR with 6. 3 is I think 0, 1, 1. We will get 5. See, in case of addition and XOR, if you keep adding same input, output is changing. But in case of this minimum maximum GCD, your output won't change. Keep adding 6. Maximum will be always 6. Minimum will be always 5. GCD will be always 1. Similarly, so these functions are non-idempotent functions and these functions are idempotent functions. Similarly, one thing, what we are doing simply, we are combining the answers of these two segments. If I have the minimum till this segment, and if I add the contribution of this segment, what this segment is doing, it is adding the contribution of this elements. We have till this much, so we are getting the contribution of complete segment. That is a good thing. But this second segment is adding this extra part again. But will it affect our answer? No, because as we see, this was already the input for our this range, and you are again giving this part as input. Will it change our answer? No, it won't change. And it's common sense that for this segment, if we have minimum m, and if I again give you this part to find a minimum, will no, because for finding m, we have already considered that part. So if you again give me that part, my minimum won't change. Yeah, but if you give me this new part, it may happen that here there is some element capital M which is less than my m. So in that case, my minimum will change. But we want that change because we are calculating answer for range from 0 till L. So we want this change, okay? Because we need to find the answer from L till L to R. So we want the contribution of this part also. So in this way, idempotent functions, the answer won't change because of the contribution of same part. But for non-idempotent functions, the answer definitely changes. Okay, so if you ask me, depends upon the type of question. If you have an idempotent function given in the question, you can answer queries in big of one. If the function is non-idempotent, you will simply answer in log n. Okay, and you know one thing. Usually, like if we have a non-idempotent function in your question, you will never build a sparse table because for non-idempotent functions, you can remove their contribution, which we can simply do using a prefix array. So there is no need to build a sparse table for non-idempotent functions. For idempotent functions usually build a sparse table. Well, there are some cases in which you need to iterate over the range also. I will tell you ahead in the video while emptying this sparse table. But in most of the cases, you will be implementing this sparse table for idempotent functions to answer your query in big of one. Okay, fine. I hope so. You guys are clear with the working of sparse table, how queries are processed, how we build a sparse table, and time and space complexity. Okay, we didn't discuss the space complexity. Um, Now it's pretty simple. If you are building n law or you are okay, this is our time complexity because this many elements we are calculating in sparse table. Now, if we are storing this many elements, of course, we will need this much space. That's why space complexity is also n times log n. This is our time complexity and this is our space complexity. But that's same because since you are calculating answer for this many elements, you are storing this much elements in your memory. You are creating a matrix of this size, and your space complexity is also this. In code, usually, yeah, okay, same, no change in this. So this will be a space complexity. Now let's move to the code part. I will be coding sparse table in Java, but for C++ users, I will be providing the C++ template in description. You can find my GitHub link. Java code will also be available over there. Okay. Now let's implement this. Let's implement the sparse table. I will be implementing in Java. Before start the implementation, I would like to mention one thing. In last part, I mentioned that usually sparse table is not used for non-idempotent functions. But I also mentioned one more thing that it's not always. In some cases, it's used. Um, One of the case I would like to mention is of range product. We know product, okay, product function, novel product multiplication. Now you can absolutely create the prefix arrays for product. You can create it and you can answer queries in big of one by removing the contribution of product from L minus one. It's possible. But the thing is, your complete story changes when there are zeros in your array. Let me show you an example. Let's say you have an array like this 2, 3, 0, 1, 8. And if you create a prefix product array for this, it will look like this 2, 3 to the 6, 0, 6 is 0, 0, 0. Everything will be 0. Now the array is constructed correctly. But the thing is, if I ask you the product in this range, you will answer me 0, even if you remove this contribution. Okay, but the actual answer is 8. So in such cases, you can use sparse table. So there are some cases for non-idempotent functions also where sparse table is used, but mostly for non-idempotent functions, we don't use sparse table. Okay, let's start implementing sparse table now. So I will create a class sparse table. So we'll be having public integer m size of our array, then sparse table public int a to d matrix. I will denote sparse table with st. One more thing we need, that is the log array. I didn't explain anything in complete about log array. What is that? Why we need it? Now I will explain. Okay, log array we need. Let's create a constructor. Okay, integer our array. Okay, let's create the object of our sparse table. It would be n. Okay, we need one more thing, that is max par. That is, what is the maximum power of 2 we need? Like, we will be having an array of length n, and for declaring the second parameter, we should know the mag j. Okay, we should know j such that 2 to the power j is less than, not less than, your, I think, n must be less than equals to 2 to the power j. Yeah, we have to determine this j such that 2 to the power that j must be greater than or equal to n, because on that basis we will declare the size of our sparse table. Usually people declare it as 30 or 32, as I told in video, but let's determine the actual power which we need. So while when left shift by max power is less than equal to n plus plus max power. Simple. So this is something 2 to the power 2 to the power mx power. So one left shift by max power is equivalent to writing 2 to the power max power. Okay. Once we get the max power which we need, we'll create our sparse table. Then we have our log array also. First, initialize the sparse table with default values. Now we are building a sparse table for finding minimum, so we will initialize it with a very big value. Currently, we are dealing with integers only, so I will be declaring the max value of integer. If there is long, you may declare long max value. Java, and in C++, I think it's L. For int max, there's int max in C++, and I think for long it's like L long max, something like this. I don't remember. Since we have fill our sparse table with some default values, now one more thing we need to do. Let's calculate the log array, and I will also explain what is the log array. Let me declare the base case log of 1 equals to 0. So I equals, let me create the object of log array. So log equals to new, and it will be of n plus 1 size. Don't worry, I will be explaining everything. Log of equals to log of I by 2. That's 1. And then we will call a build function. We are done with n, st, log, and maxpa. So here we will be having public void build function. And one more function we need to calculate is public void, not a void. It will be a query function which will be L and integer r, and it will return our queries. Okay, fine. So what is log array? Let me see whether it is recording on. Yeah, it is recording. So let's understand log array and why we are using this log array. If you guys remember, when I was explaining you big of one queries in a sparse table, I mentioned that, let me have it, yeah, what I mentioned at that moment, that we don't iterate over all the paths of two. What do we simply do? We consider two segments. Let's say here is your and here is your R. we will be considering two segments of length 2 power j such that it is the largest power of 2 which will fit in our range L to R. Okay, I explained this earlier and I also explain why behind that. Now, for any random range, we can get any random range in input like 7 to 16, 5 to 19. Now they can have any lengths. 9 minus 5 is somewhat 15 plus 1. Okay, the length of this segment. And the length of this segment is simply 10, not 10. I think its length is, yeah, 10. Its length is 10. So we can have any different lengths. So you can do simply while querying, you can calculate the length, and what I did here, you can simply run this while loop. In logarithmic of n time complexity, you will get the maximum power of 2 which will fit in a range, and you can simply answer the query. But it completely eliminates our agenda of answering the queries in big of 1. We will again require an log n time complexity to answer the queries. So it's better we should pre-compute some data which we will directly use at that moment. Now just think what data we actually need. The data we need is, if I give anything input, let's say this is my L is length. If I give any length in input, I must get the maximum power of 2 which can fit in this length. This thing we need in output. Okay. So this is the purpose of our log array. A log array return as the maximum power of 2 which will fit in your length. That's why you can simply see I have declared log array of size n plus 1 because at max we can have length till n for an array of n. That's why I declare log array of size n. Okay, and you can simply see that the base case log of 1 equals to 0, that is for a segment of length 1 the maximum power of 2 which can fit is 0. Okay, because 2 to the power 0 is 1, and that is the maximum power which will fit. So that's why I wrote this base case over here. Then I calculate for rest of the elements or rest of the lengths from I equals to 2 to I equals to n using this formula. Let me copy this. Let's see whether it will get pasted or not here. Okay, it is getting pasted. Fine. So using this formula, I'm calculating for a segment of length I, the maximum power of 2 can fit inside it. Okay, now let's see how this formula is working. Okay, so let's start from here. Consider log, let's say log n to the base 2 is equals to k. Okay, log n base 2 equals to k. It means constructing this number n, we need a pass k pass of 2. It may be in decimal also. It may be in decimal also. Here in our code, we are dealing with integer values. That's why I will write here flow value. Okay, we are considering flow value because of course we need integer parts of 2, not in decimal formats. Now, can we write this equation like this? 2 to the power k is greater than equals to n less than 2 to the power k plus 1. Of course, we can write this equation like this. Um, let's not consider n, let's consider I. Since we are discussing in terms of I, let's consider I. For any length I, we can write equation like this, that log I to the base 2 equals to k. Okay. And you can write this equation like this. Of course, if we need two I k parts for constructing I of 2, we can simply write it like this, that 2 to the power k can be greater than or equals to I, and this I will be of course less than 2 to the power k plus 1. Let me show you by a simple example. Because in last video I got a feedback that my mathematical proofs were very confusing. So this time I'm giving some examples so you guys will get it. Let me think about an example which we can take. Let's take a 10, simple example. Let's say your I is equals to 10. Okay, its flow value is 3. Correct? Its flow value is 3. Now, of course, you can write like this. 2 to the power 3 is less than equals to 10 is less than. Here we cannot include a sign equals to because let me write it 2 to the power 3 plus 1, which is 4. This is 16. This is 8. Okay. Now, for perfect powers of 2, sometimes it may happen instead of this 10, we get a perfect power of 2. So this will come out to be 4, and you will write here a 4. Okay. So that's why using equal to sign, but not always we will get we will get a power of 2 number, which is a complete power of 2. So that's why we have included this greater than sign because for 10 it will be something 3.3 something like this it will be. So that's why we have this greater than sign. And of course, if we remove this decimal part, this is the power just less than 10. Then the power of 2, let's say this is equal to j. 2 to the power j is the smallest power less than equals to 10. Then after 2 to the power j plus 1 will be the number which is strictly greater than 10. Okay. So on this basis, I write this equation. I hope you guys get why the equation is like this, or you can say inequality. Now do one thing, divide this equation by 2 on sides. We have 2 to the power k divided by 2 less than equals to I by 2 less than 2 to the power k plus 1 divided by 2. Okay. Now let's rewrite this inequality correctly. Okay, you can write this inequality like this. Now, since I by 2 may be in decimal format, if I is odd, then I by 2 will be in decimal format. So that's why I'm taking the flow value. Okay, I'm taking the flow value because of that reason. Because dealing with integers, so there's no point of considering the decimal values. Um, I don't have enough space. Maybe I can use another slide, but I need to switch back again and again. So, okay, let's create a new page. But so what equation we were having earlier, that is 2 to the power k minus 1 is less than equals to I by 2 flow value is less than 2 to the power k. Okay. Now, what you can do, ignore this part. Now we will deal with this inequality and take log on both sides. If you take log on both sides, the equation will look like this. K minus 1, okay, k minus 1 is less than equals to log of 2, yeah, I by 2 flow value and flow value of log also. One more, I have one more reason that why we consider flow value here, because you see, usually while writing, when we write I by 2 here, it results into an integer division. That is also one reason you can consider, but I think the first reason is more sensible. Okay, so you can write this equation like this. Now, why I take flow value for again because our k is 2 to the power k was a power of 2. It's an integer. So of course k minus 1 is also an integer. So that's why since this term is integer, I took the floor on our RHS. Okay. Now, since I'm taking floor on this side, we can remove this greater than sign and we can directly write k minus 1 equals to log base 2, and here we will be having I by 2 its floor value. Now I know a lot of you may instantly get it out that why how we directly remove this greater than sign and it equal to over here. See, again I need to take an example and just remember some past things which I told that. Tell me one thing. See, tell me one thing. As we know, this 2 to the power k minus 1 is the just smaller power with respect to I by 2. Okay. This power is, or you can say this is the largest power which is close to I by 2. Okay. Largest power of 2 which is close to I by 2 or lesser than equals to I by 2. We can say this. Now, now, tell me if I we calculate I by 2. We take its floor value to an integer over here and we calculate its logarithmic value to the base 2. Let's say we get that value in decimal format, but we take the floor. Although I should not write floor here, and we took floor and it gives us an integer 3. Now tell me one thing, what I said earlier that this is the closest power of 2 which is less than I by 2, which is less than I by 2. So if I take floor of this value, of course our value is equal to that power na? Because how now of course lot of you may again will have a doubt how that power will instantly get equal. Just remember what I said earlier that we are considering an n which is less than equals to 2 to the power k and greater than 2 to the power k plus 1. Now what I said, this n may be equals to this 2 to the power k, or it can be between 2 to the power k and 2 to the power k plus 1. It can be between, even we saw the example of 10 that 8 is less than equals to 10. We saw this example. Now tell me one thing, divided by 2, you got 4, 5. You calculate the log 5 to the base 2. You will get something 2 point. And if you get log on this side, you will directly get 2. Now this will be 2 point something 2 or 1. If you take floor, of course this value will be directly get equal to this 2. Na? I hope you get what I wanted to say. Like just connect the things which I told earlier. Just connect the things. Try to connect the things that I'm telling one more time. See, let me go to previous slide. See here. We start with log I to the base 2 equals to k. We take floor because we are dealing with integers. Now, what I said, if we need a k powers of 2 to construct this I, then of course I can write like this. Even I said that it may happen that 2 to the power k is directly equals to this I. That's why we have included an equality sign over here because it may happen that I is a power of 2. Then we simply divide all sides by 2 and we got this equation. Yeah, we got this equation. And I again take flow over here because I said we are dealing with integers in our code also. That's why I take a flow value over here. Nothing changes. Everything was same. We divide on both sides by 2. Now, what happened? Okay. Now we were with this equation. What I said, take log on both sides. Once you take log on both, the equation become like this. And then I just take flow over here and I remove this greater than sign. Just because whatever number you have, it is that power of 2 plus something, okay, because our 10 was 2 to the power 3 plus some values, but But on taking log, since log 10 to the base 2 is 3.3 something, but we take the floor value, so we remove that decimal part. That's why whatever we get directly becomes equal to our LHS. Okay, what you can do simply, write just revolve part and write everything on paper and try to think on them. I know you will not get it directly, but just rewind this part and try to write these equations by yourself. You will definitely get what I wanted to say. Simply, now what you can do, you can write this k equals to log I by 2 floor value plus 1. Now remember, k was equal to yeah, this term, log I to the base 2. So we will write over here log I to the base 2, its floor value is equals to log I by 2, its floor value base 2, floor value plus 1. Don't confuse because of this floor sign, because in code we at every place are dealing with integers. That's why I'm writing floor over here to be more mathematically precise. Okay, fine. So now you get how this equation come, that what this equation is denoting, the maximum power of 2, sorry, what this term is LHS is denoting, the maximum power of 2 which will fit in a segment of length I is equal to log of I by 2 to the base 2 plus 1. So that's why in code I have written log of I by 2. Of course, this is an integer division floor. This is also an integer plus 1. Okay. It seems unintuitive at first. Even you can draw this area on notebook and see that we are getting how two parts of 2 are constructed. Okay. Now let's write the build function over here. What I told while explaining the build part, that we start from the smaller parts of 2. Well, I forgot one thing, that for integer I equals to 0, st of I comma 0 equals to ar of I. As we saw while the building part, that 2 to the power 0 1 is the element itself. Okay, so I write this base case. Now we will start from j equals to 1. J must be less than max power, which we already calculated, plus plus j. Let's iterate for the elements. Now till which point we should consider. You cannot write directly. Okay, let me write the equation first. St of I comma j equals to math dot mean. Remember the formula, st of I j minus 1 comma st of I plus left shift by j comma j minus 1. Okay, I have already explained this formula in a previous part, so I'm not explaining this again. Huh. Now see here, what we are writing, I plus 2 to the power j. Okay, and this are the nothing but the number of indices in our array, and they must be strictly less than n. So we should write here left shift by j. So we want get out of index array exception, out of array index exception, sorry. And that's it. We are done with the build function. Let's test it. Public class ps public static void main. Let's take an array integer equals to, let's take the same array which we take in building, 37281 37281 94615 94615. Okay, let's create an object of sparse table. Sparse table ARR dot length for ARR. Okay, now if we build this parcel, let's check the output. Okay, here we will print the pass equals to 0, j must be less than, I will say, st dot max path plus plus j for y equals to 0, I must be less than n plus plus. So s out st dot st. Okay, so define st dot n. Okay, so st of ij. Okay, let's run this code. Missing return statement. Okay, I'm not returning anything or return 0. Okay, now why did it printed like this? 3211. Oh, sorry. I'm really sorry for this mistake. Okay. Now you can see we got same output 3321, 7211, but we got 7766. So for length 1 it is 7, for length 2 it should be 2. There's something wrong. J equals to 1, just less than max power plus plus I equals to 0. Um Even this is also correct. Plus plus I. St of ij is the Maillard mean of st of ij minus 1 and st of I plus 1 divided by j. Even the equation is also correct. St of ij minus 1 I plus. Okay, I here it should be j minus 1. Yeah, now we are getting correct output, and you can compare 3321, 7211, 21 an empty value, 7211, 221 an empty value, and 811, 31914, 811, 31944. Okay, so our build function is working correctly. Now let's write the query function. Now query function is even easy and small. We have to just return math dot mean of those two values. Now here we will use that log array to find the. First we will start from our L. Okay. Now what is the largest power of 2? Integer largest power equals to log of the length of our segment is r plus 1. So this is the largest power of 2 which will fit. So just simply write your largest power. Now for r we need to come that many terms behind. So you need to write largest power first one and largest power. That's it. Let's check this also. Mm, Let me remove this. That's out. Query. Now let's find the minimum in range first. 0 to 3. Query. Let's find in range 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5 to 9. Okay. So 0 to 3 the answer must be 2, and for this the answer must be 4. 0, 1, 2, 3. Well, how many answer 1? Answer is for this 0. I need to let me see for what read output. Well, we are getting wrong out. Um, okay, I got the reason because we need to write r minus 2 to the power that largest power, whatever it is, plus 1. I'm doing logical errors today. Not today, I usually. Okay, I didn't correctly do. Fine, so 0, 1, 2, 3, 4, 5. Let me check for this also and change this. Let's check for 8, comma 9. Okay, there's something more wrong with this. For 8, comma 9, we are getting. Oh, what's wrong in this equation? L, then we largest power, st, comma r minus. Everything seems correct. Let me check over here. Even this is correct. Lj, yeah, even I have written exactly same equation that r minus, yeah, r minus 2 to the power that power plus 1 and that power. Even this is correct. This is correct. Everything is correct. Then what is wrong? If everything is correct, what is wrong? The build function is working correctly. Even this is also correct. Then still why we are getting such weird outputs? Um, okay, let me write this. Let's check this output again. And now this time, okay. Now I will print the query also as out st dot query, and it was from 8 to 9. Is the length 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's wrong over here? Now we are just getting this large number, 5 and 5 for a length. Okay, so we can see here must be 5, but yeah, so I comma j minus 1. Uh, Let me. Okay, it was a very small issue that I just need to add here a minus 1. And it was very simple because I plus 2 to the power j minus 1. Okay, minus 1, this small thing I didn't notice. Okay, not a big deal. Fine. So now you can see we got the output 5, and we have a 5 over here. Okay, so this is how you will write a sparse table. This is our constructor, this is build, this is query. One more key function I would like to mention. As explaining, I showed that we will iterate over the pass of 2. How we will do that? See, create an integer s equals to integer dot max value. Okay. Now let's calculate the length. Length equals to r minus l plus 1 less than 31 plus I. So now we will iterate bits. We will iterate over the bits, and even we need our index equals to l. Even there is not need for this. We will start from bigger pass because we need to consider the largest power from our help and everything while explaining the query part. So if you don't remember, please watch that part again. So your res equals to math dot mean res. First, if your len left shift by 1 and 1, this is the thing I don't like in Java, that if statements only evaluate true and false. They don't consider 1 and zeros as truth and false values. If it is equals to 0, so that power, we don't have to include that power. Else what you have to do simply st of your current L and the power considering is I. That simple it is. And you have to move your L also. If you guys will get confused, instead of L, I will call it index. And now the new value of your index will be, since we have considered a segment of length 2 to the power I, just move your index by that many positions. Well, return your res. Okay, fine. So that simple it is. If that power is not present, just continue. And if we have to consider that power, simply consider index comma that power and move your index by that many positions. Since if we have query 1 to 10, then I think we can consider the largest power 3. So 1 plus 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, correct. Let's run this code. Okay. Out of bond error we got. Okay, so we have calculated the max power. My bad. Again, index 16 out of 1. Index 16 out of 1. Mm, I've declared here a max power and starting must be greater than equals to 0 minus I. If length left shift by I, first of all, this change I need to do. Okay, now we got 5. Correct. Let me check for 4 till 9. We should get to 1. Correct. For 0, 3. So this is another way of writing your query function. This works in log and time complexity, but yeah, correct. So, but for idempotent functions, you can simply write this big of one equation. If it is not idempotent, if it's not idempotent function, you can simply write query in this way. Okay, so we are done with sparse table. In next video, we will learn about Fenwick tree, how a Fenwick tree works, even constraints. There are some constraints that you cannot use a Fenwick tree for. We will discuss all that things out there in a Fenwick tree video. If you guys have any doubts, you can write those doubts in comments. I will try to answer those doubts there. Okay. If you guys even have any suggestions regarding my explanation or whatever thing it may be, if you guys have any suggestion that you can do in this way, so it will be better for us to understand, you can definitely write it in comments. I'm always open to suggestions. Okay. So thank you.